Thank you. Where's the clicker? In some ways, this is a continuation of the keynote I gave. I want to explain in a little more technical detail. I made the fairly bold assumption that we really bring down the barrier to entry to using confidential computer. And I want to explain that in very concrete terms with our Certifier Framework. Oh, that's backwards, sorry. There we go. And the way we'll do this is, here's what we want to do. We want to have 4 interacting enclaves, Ts, protected programs that work together to provide a single service. So in this case, as you'll see all over this conference, there's a service that generates a whisper model, a speech-to-text model, which is running in Grameen in our case. There's a server that lets clients have access to the service, namely speak, and you'll get text back. That runs in SEV. And then there are 2 clients that send requests and get it back. And those are in either Keystone or Islet, really we should call it, the ARM protection mechanisms. There's a single certifier that certifies all these applications. So when you start up, you say, here are the measurements of the programs that are trusted, and here's the platforms that we trust, and platform properties, and then you're off. So this is a very concrete way of explaining what we wanted to do. And our goal was, you should do this like really fast. Okay, so just to review the framework, each of these things that I'm going to talk about is an application that talks to the certifier API. That API will talk to the certifier service to validate that it's a trusted program within this security domain. And you're off and running. Those are I think we covered actually most of the platforms we support. I will mention once more, since it was mentioned again, SGX is an application level enclave, which has some disadvantages depending on programming. Not only do we support encrypted virtual machines, we can actually delegate to a service to provide primitives to each individual application. So it makes the individual applications confidential computing consumers. Okay, so just a very few concepts. What makes it so simple as a developer to write these programs is these sort of key concepts. So the first concept is the concept of a security domain. That's the collection of programs that agree to abide by all the rules. And the way you know they abide by the rules is to look at the code. They are bound into this domain by a single public key, which you can think of as being incorporated in the program. That same application can operate in another security domain with a different key, we call it a policy key, and have totally different rules. So the application doesn't need to know the trust rules at all. So you could write an application to share data or whatever the hell you're going to do, and the application need not worry about any of the mechanics of relying party transactions or any of that. The process of certification, we don't use the word attestation, is the process of talking to a server, which holds the private key corresponding to that public key, and say, listen, here's a bunch of evidence, including an attestation, which shows why you should trust me. The service will evaluate that, actually, as you'll see, produce a proof given the policy, and hand back an X509 certificate with a public key that was pro-offered by the application and the measurement. By the way, that measurement is the identity of the principal of that application. And then trust and policy. I think one of the things I emphasize is absolutely don't hard code trust and policy. That's all done at the certifier, and it's done by declarative rules. And typically, my advice is keep the rules simple. As you'll see, there are only 5 to 10 rules in even fairly complicated domains. The way you program this, if you have a C++ application, is you interact with 3 C++ objects and usually only 2. The first object is the object that generates all your keys, gets you certified, and saves all your private information, like your keys, automatically in a policy store. The second one is a secure authenticated channel, which can talk and verify other programs in this domain. It opens up a mutually authenticated, encrypted, integrity protected channel. And when you ask that secure channel, who am I talking to, you get the measurement of the program on the other end. Finally, if you want to, as I said, we support very complicated applications also, but typically this is all you do. There's a policy store, so you can store stuff. This is important so you can cold start. Once you're certified, you can cold start at that machine with no latency. I don't have to talk to anybody. Okay, but the key thing is the slide. If there's one thing to remember, it's the slide. I said it was easy. This is it. This is the entire interface almost everybody needs to use. The first, I guess there are two statements, but they're on the first line. It says, here's the crypto I want to use. I want to use 2048-bit RSA for authentication and public keys, and I want to use AES 256 GCM for any symmetric encryption, authenticated symmetric encryption I do. The second line says, okay, app trust data object, this is going to be an SEV enclave. I'm going to use it for the purpose of authentication at the risk of distracting people. That could also be attestation. That application enclave service actually gets certified to provide attestations for other people. Most programs just say, I want you to authenticate me, prove who I am. And then finally, the thing called store is just where the file is stored, the encrypted policy store. The entire interaction with your program is the following. Initialize the enclave. Each enclave has a very slightly different initialization routine. We do that all for you, just apply the arguments. For example, SEV wants to know the ARC key, the basic AMD key. The second statement says, give me my policy key in case I have to refer to it, like when I open a secure channel. The third statement, called cold init, says, okay, make up all my keys for me and save them. My public key, my symmetric keys that I encrypt stuff with, do that. And the fourth statement is sort of the key statement for confidential computing. It says, okay, now make an attestation with my authentication key that you generated, and pass that together with whatever evidence you need to the certifier service. And the purpose of which is to get back that certificate. I told you, to prove that I'm trusted within this security domain. That's it. I also, to distract you a little further, here's the authenticated channel interface. The secure authenticated channel is an object, and it can operate either in the server or the client role. It's in this case, client. And once you init it, you just say read and write to that. If you want to put an API on that, you could do that too with a Thrift or the Protobuf's API interfaces. Okay, so one of the ways we show people how easy it is to use it is we implement the very same simple application for every platform. And we call that creatively Simple Example. Simple Example runs on every platform. And if you looked at it, most of you would not notice the difference between any of the implementations. It's really quite portable. Simple Example, the thing it does is very simple. You negotiate trust, you do your certification, and then the client server says to the, first, the client says to the server, hello from your secret client, and the server says back over the secure channel, hello from your secret server. But obviously, you would do more complicated things there in your application. That's it. So when I say 15 minutes to adapt an application or a service, that's what I mean. Those things and nothing else. You don't need any other infrastructure. It doesn't depend on the cloud provider using token X or Y or Z. You can do that, but you don't have to. That's it. You might want to add a few things to that. So for example, as I mentioned, the secure channel, instead of sending data, you might want to do API serialization, make calls over it. Again, just connect Thrift or Protobuf. We use Protobufs. You might want to ACL things for differentiated access, like, okay, there are 5 programs in this trust domain, but security domain, sorry. But that program with that measurement can get this data. That program with that measurement can get this other data. And it's very fast. It's ACLed. It's not a public key operation. And you might want to also implement some standard distributed programming primitives like commitment. It depends on your application. We work with a simulated enclave, so you can develop without any hardware at all. AMD SEV and SMP, Intel SGX, Grameen, which is quite nice because it makes the programmer's job look like he's just writing on Linux. Open Enclaves also does a nice job, but it exposes a little bit more of the SGX mess of the last speaker talked about in calls and out calls into the enclave. ARM CCA that Samsung contributed, thank you. RISC-V Keystone, we will do TDX. It shouldn't take long. We haven't done it yet because the version of TDX that we see publicly doesn't support all the primitives. We can do a hack to fix that, but we haven't done it yet. And then the application enclave that I mentioned, that you as an application, a process inside an encrypted virtual machine can implement stuff. I didn't keep track of what time I have. So anyway, so just let me do a brief summary. The Certifier API is simple. 95% of programs do exactly what I said in that little slide and nothing else to use confidential computing. We can worry about rotating keys and all that stuff. It abstracts all the stuff that confidential computing provides. So you don't need to know whether you're on ARM or Fred or whatever. And that's really important for adoption because there's no single platform that's widely used right now. So in order to get people to use confidential computing right away, as I would like to do, you better support everything. It provides a secure store, so that's all automatic, and a secure channel. It's almost simple, as simple as I said earlier, as Hello World in Linux. I love Linux. I actually was at Bell Labs for the Unix thing. That's the model. It's like copy and paste this program, stick other code here, but get started right away. That's the idea. I'll say a little bit more, which I didn't touch on in the keynote, about the Certifier service. It's a centralized, it's actually distributed, but you talk to a Certifier service to evaluate all rules, rather than doing it locally. I will tell you a big secret, they actually can evaluate locally also, but we recommend against it. It's all policy driven. You don't write code to say this is how you do relying party claims. You just write rules, and I'm going to show you the rules in a second. The advantage of this is you can add new components. It's very quick. All control delete sort of new program is very easy. You can upgrade applications easily. It facilitates data migration, a whole list of things. It's easy to do. And as a result, it provides us scalable for every 9 of resilience you want for the service. You just add another server, roughly. Deployment for all environments. As we talked to one cloud provider, and they say, what do people have to do to use on our cloud? I said, you don't have to. What do we have to do? The answer is nothing. Just give them the hardware and let them talk to the internet. You're done. And you can do more, but you don't have to. I will give you an example of the policy. I mentioned an English-like, and you can argue with me if this is English-like enough. Policy language is based on the Lamson-Abadi calculus. So let me just read the rules briefly. The first rule is really an axiom, not a rule. It says the policy key, the thing that's associated with the application, is trusted. Anything it says, you should believe application. The second rule says, well, in this security domain, the policy key says this measurement, which is the identity of the program, of a program you trust, is trusted. So if that's the measurement of program, it's trusted. The third statement says the key of the hardware provider that appoints the attestation key is trusted, like the ARC key in SEV. And the final statement, which actually comes from the platform, not the thing, is that the platform key says the particular attestation key that makes the attestation is trusted for attestation. That's it. 4 rules. Now you can argue whether that's English readable or not, but it's unmistakable. The actual everything's in there. If we say a key, it's the whole key in there. If we say a measurement, it's the entire hash of the thing. There's absolutely no ambiguity. And the Certifier service evaluates this and actually produces a proof. So for example, when you make an attestation, typically you hand up a public key, which we call your authentication key. After you're certified, from then on, that's how you prove who you are and how people should trust you and how you open up authenticated channels. This is the actual proof that the certifier produces and actually can log or send it back to you for why we trusted your program. And I will just read 1 or 2 lines from that. The first line is, the policy key is trusted. That was one of our rules. And the policy key says that measurement is trusted, so the measurement is trusted. those kinds of simple rule evaluations. And the output of all this, in the end, is, well, the key, the program authorization key that was offered up in the attestation, the thing we generated with cold init, is trusted for authentication. So from now on, any program in this domain, if that authentication key signs something or says something it's true, you should trust it as you trust the underlying program. By the way, that's signed by the policy key. We don't rely on any PKI except stuff embedded in the program. So you don't have to worry about Fredco getting compromised. That's it. We can also evaluate platform properties. There are two things you want to evaluate in an attestation. One is the program measurement, but secondly, you might want to evaluate things about the platform. This is a policy for an SEV machine. So for example, the policy might say, for SEV, I don't want other applications to be able to debug the application on the machine because they get secrets then. I don't want the application to be automatically migrated. I want to control that myself. The API to the hardware has to be of this level. And there's more junk in the TCV version that I won't explain in great detail, but that's it. So we evaluate both platform characteristics and measurements, and that's really all you care about. OK, so now one more time, I'll summarize Certifier service. Simple policy language, readable, standard evidence formats. We don't do parsing. We use protobufs, so no parsing mistakes when you evaluate rules. Evidence is submitted automatically. You don't get in the middle. If you may never hear the word attestation. If you're a programmer, you may not have to know that word. We provide utilities to generate keys and write policy. It's actually quite simple. Anyway, that's it. That's it for the Certifier service. And now I'll bring up a real-life programmer who talked through the final 3 slides, Ye Li.
Yeah, thanks. So I'm just going to go back to the example John gave at the beginning of the talk a little bit more. Where I guess the takeaway here is basically 2 things. The first is the use case. I guess a lot of people here kind of a similar use case in the morning. We're kind of assuming that we have a speech recognition model based on Whisper that's kind of a secretive and cannot be basically provisioned in clear text with the image that you deploy with the service host on the cloud in an untrusted environment. And the assumption here is that we are going to deploy that speech recognition service in an untrusted cloud environment where it contains all the servers, for example, the web servers that you can use to do the speech recognition and the client server code there. So the deployment image will not contain the model itself. Instead, it's going to be brought up and then get certified through the certifier service. And eventually, the endpoint will just, the model provider will transfer the model through the secure channel set up by the certifier service to the service host. And then on the consumption side, we will have different clients that's going to be able to send requests to the service host to get the transcript for the audio file. And in this image, you see 2 different clients. One of them is based on RISC-V Keystone, and the other one is ARM based on CCA and the iLED SDK from Samsung. In the actual demo, we also have basically a web client, which is basically communicating to the server through HTTPS instead. So that's the kind of a use case which reflects some of the kind of a common scenarios that we envision. But the second thing that I want to focus for this demo is the fact that we are trying to demonstrate cross-platform capability of the certifier, which is, as you can see, we are trying to set up an environment where we have clients from different T platforms. The model provider, for example, is running on top of Intel SGX, which we actually, in this demo, is using a Grameen SDK to implement that server. For the service host, because of all these server setup, we actually adopted the encrypted VM approach, which In this case, we're using AMD SCV SMP. And for the client, in addition to the HTTPS client I mentioned, we also have the ARM and the RISC-V clients, which will demonstrate how Certifier would be able to kind of support this scenario. So drop by the demo booth, and we'll show you how, for example, the Certifier service policy for this trust domain can be set up with this example, how it can be extended when new clients are added, and what exactly is the policy looking like for this exact setup. Finally, oops.
No, you went backwards. I did that.
Right. So yeah, for the Certifier framework, we are going to conduct more severe, more strict security reviews as we go. And we are also considering the support of GPU platforms. For example, NVIDIA Hopper GPUs. We're also thinking about adding Python bindings for more kind of approachable AI machine learning use cases. And then, the Rust client support is also on the way. Essentially, it's an open source project, so anyone interested can go take a look. And we welcome people to basically, use and contribute, bring up issues, and also help with the security reviews also. Right? So with that, thank you.
I don't know how much time we have for questions, but I'm happy to answer questions.
Sure.
Yeah.
I have two.
Okay. You can have as many as you want.
First one, have you given any thought to federation of attestation between organizations? And second question.
So the concept here is is for any particular objective, you would typically have all the parties contribute to a centralized certifier service. That's the easiest thing to do. So everything I said about 15 minutes works if you do that. You can actually have a program which sits in many different policy domains. That's another way to do it. But in almost every application I've seen, it is known in advance which programs you want to collaborate in a specific activity. And the easiest thing to do is just set up a certifier service where everybody approves the rules, where you know all those programs, and then it's like 15 minutes.
Right.
So there are two ways to do it.
You have to trust the certifier service somehow too.
Huh?
And then you have to trust the certifier service
You have to trust it in the following sense. We give you the code, so just like any program, you know that. You can run the certifier service in Enclave, and you can run it under conditions where you could prove to anybody, say, listen, I can't see anything. The rules are your rules. I don't even know the private policy key. Only my certifiers know it. That's it. So yes, you do have to trust the certifier service, and there are many ways to trust it. One is it's running on a machine under my desk. That's not the best way, by the way. The other is the one I told you. You would stick it in a confidential computing enclave and make sure everything was protected. And everybody who relied on that in a security domain would send rules and interact with that service. But nobody outside gets to see it, and even those individuals get to change the behavior of that.
Okay. So my second question is, speaking on behalf of administrators everywhere,
yes.
Is there anything in the policy language that you are creating for this? Something that, say, Rego doesn't support?
That has what, sorry?
That Rego does not support.
What's Rego?
Rego is a universal policy language for OPA, basically.
Yeah. So we can support other policy languages. We typically don't recommend it because the policy really is that simple, and we want them to be readable. And it doesn't take hardly any time to write it. But if you're stubborn and want to use another policy language, you can.
Yeah, it's more than stubborn. It's every time you have a policy language, then you need to have a validator for it. You need to have all the governance around it.
Most policy languages have very complex validators, which I don't want because they can make mistakes. That's one of the reasons we'd recommend against it. And also the policy in some of these is written in this crazy style. I don't know what the hell it means. It's like, it's JSON-like format, and here's some tag, and you're supposed to know what that means. Here's some other. It's like, oh, okay, you can do it if you want, but Jesus, I wouldn't do it because I don't understand what it means. But yes, you can't substitute a policy line, other policy. And God help you if your policy is complex enough to need a complex policy. I think you're already in a state of sin at that point. There's a question here, I think. Oh, there's a question there too. There's a question there too.
It's a follow-up on what Mark asked, right? So if I'm a programmer trying to parse this policy and make sense of it.
Programmers don't parse the policy. Only the certifier service does. Applications don't touch that policy. They don't have to know anything about it.
Okay, so I'm trying to fit in a kind of a KMS type of a flow where I have to release a key if this meets my security and the policy that I have defined. If at what part? So this looks like a net new policy language.
Little new. For the KMS is actually an interesting one. We've actually implemented that. So there's a basic service, and typically what you do is download an ACO list, which is signed, saying this key this key is associated with this measurement, which is extremely rapid. So you can put a much simpler access control system on top of this. We actually implemented that, and it was one of our examples of something you could do very quickly. You could also use an HSM, but.
Okay. My next question is, like if I work for Azure, so.
Attaway.
So we have platform level firmware baselines, right? What we are running. That's part of one of the important claims that a relying party has to use to certify if this, you can release your secrets. In this hosted service model, I'm trying to understand who's going to provide that baseline.
Okay. So that's a
and
good
how
question.
are you going to communicate?
So first, this doesn't have to do with SGX, which are application level. This more has to do with SEV for encrypted virtual machines.
Yes.
Mostly. And there are two answers to that. When you come to our booth, you'll see a thing where we validate everything from the bottom up. So you'd provide measurements for that. The simpler and better way to do it, and the reason we do that is some lift and shift applications, which, by the way, I don't trust the security in lift and shift at all. But if you have an application written for or an SEV, entire pod, I guess you'd call it, written for confidential computing, what you really want to do is direct boot, in which case you don't care about measurements except for a init RAM and the kernel and maybe a small BIOS. And then you can do that yourself if you're a customer. But we support both models. Go ahead, kill yourself with measurements at lower level stuff if you want to, but I'd be extremely cautious about the security of complicated measurements. You can do it, no judgment, but there you go.
Okay, yeah, cool, thank you.
So my question relates to the evaluation, auditing, and forensics around policies, which really need to be human readable to achieve anything. Cryptographic measurements are not human readable, and we have a long-standing tradition in the software world of using names and versions to identify software.
Using what?
Names and versions to identify software.
Right.
So have you given any thought to how you might
So the short answer is yes and no.
map measurements to releases of software?
The short answer is yes or no. You can securely associate a measurement with a name if you want to, but names are not secure unless they're authenticated in some way. In the end, the only thing that can be authenticated is the measurement. Now, we're not expecting people to know the measurement, by the way. We're expecting some program or some policy to expressly say that. We've limited what we want policy to understand to exactly it matches this string. We can actually provide labels too, they're, basically a level of indirection. But if you do labels, you better make damn sure the labels strictly correspond to the actual measurement. Thank you.
Yeah, so I have a couple of questions. First question would be related to the scenario where you have kind of multiple organizations that are mutually distrusted, So how does the authentication work in a case of maybe one organization setting up or who will set up the service, and how that will work so that they all get the attestation without necessarily
and again,
trusting each other?
there are exactly two ways to do this. The first is you get together with all the people you hate and don't trust, and you say, we're going to set up a certifier service together. All the keys are generated inside the certifier service, inside an enclave. No, none of us know it. And the certifier service will only believe policy signed by all of us, for example. Okay. So that's it. That's the easiest way to do it, and then everything I said about 15 minutes is true. What you can do instead is you all set up a certifier service. You all have different policy keys, and the API can say, okay, I trust this policy key to evaluate this thing. But that's more complicated. People make mistakes, so I'd be careful about that. So you can do it either way.
Okay, so two very short questions. One is you mentioned what would be the format of those attestations? How does it relate to the work from the RATS group from ITF?
Yes.
So that's one. The second question would be also related to the.
Could you put up the other diagram?
Would be related to the work here. You say you will be open source. You open source it. Will it be maybe open source through the confidential computing consortium?
Yes.
Okay.
So the answer to
sorry, one more remark. Yeah, just on a remark you made that you don't trust lift and shift. If I understand, you don't trust lift and shift approach.
Well, sorry, so, I don't think it provides very much more incremental security. Some.
Yeah. So if I just to see if I understood well. So when we have SCV, for example, VM-based confidential enclaves, that, in your opinion, gives us less, trust, because if we have
No. You can have a simple, SCV can host a simple OS that you're quite confident of with only enumerated applications in it. And so it has a much smaller TCB. Let me ask your first question first. I don't know if we put up our diagram. Nothing I said mentioned RATs or anything else. Attestations are done by the certifier service and often evaluated, even if they're talking to other. So everything I showed you, nobody, the developer and the policy guys, don't know the word RATs at all. We know the word RATs. The certifier service talks to the RATs protocol. In fact, Open Enclave uses it. But if you wanted to use another attestation format, that would be just fine. And for something as nice and simple in SEV, there's no attestation format. It's quite simple. So the answer is sort of, I guess the marketing answer is we support all those standards, but we don't want you to worry about them. We'll take care of it.
Yeah, I want to add a little bit to the RATS model thing, which is...
I can't see who's talking.
So,
I'm sorry, yeah.
I want to add a little bit to the RATS model thing because, we are not basically limiting the certifier service to the verifier role of RATS, essentially. And the kind of source of the project is really, we're looking at RATS model and we're using a verifier, in this case, specifically Open Enclave, for example.
That's right.
And
so if you had RATS 4, we'd have a RATS 4.
And we find that the relying parties still have to do a lot of work, of course.
Yeah,
if the verifier throws the claims out, we still have to parse it and make a policy decision and everything. So the certifier service really, the certifier framework is really kind of a verifier and plus the encroaching into the relying party kind of facilities so that we make the relying parties' life even easier. I would put it that way.
But I hope I didn't offend any lift and shift people, but there we go.
The question was more about the amount of trusted.
No, that's exactly the point. If you do a lift and shift, there's a tremendous amount of code that was written without security in mind. Those has vulnerabilities. Confidential computing doesn't do you any good for vulnerabilities that you can tickle from the outside. So it's important you write your application so they understand what's secure and not, and keep them as small as possible. Sorry, you know that. Yeah. Okay, there's one more question over here.
Great presentation, very cool ideas. I was wondering who's using the Certifier Framework today?
We're mostly using it internally. We have a bunch of partners who are starting to use it. Berkeley used it. I think Samsung is using it a little bit. There are 2 projects at Berkeley. There's one possible customer I can't talk about, high security applications. This is a little bit our coming out party. So talking to ISVs and people who develop programs, it's us. I should make one other point. The other differentiation is our framework works no matter where you are. Whether you're a client in a cloud, you're just porting an application on a server. It doesn't matter, any of that stuff. And we've ported a bunch of applications ourselves. I think there's a hand up there, but I can't see.
Yeah, so for my use case, I'm a little concerned about sort of the external certifier service because it sort of seems like you end up having to...
It's not external. You control the certifier service.
Well, in the sense that it's not running locally with each...
It can.
With each app. So I guess... okay, so I'm sort of interested. You sort of said something about you could embed it, but that's problematic. And I'm curious, like if I'm running a mobile app and I have to embed it... No, it's not problematic at all.
Okay. Yeah, so I'm saying it's your choice. I might say, for example, here's something you might say. I'm going to let Google run my certifier service. This is independent of whether it runs locally or not. I'd say, well, you know, for me, I want to make sure everything I can evaluate myself. I don't think that's a great idea, but you might, and Google's a good company that cares about security. Maybe that's okay. We don't make decisions, but it is absolutely true that you, the user, the guy who's running this infrastructure, if you choose, you're in control of every single bit of trust information. Nobody can do anything without your okie dokie. Sorry, I think there was another hand, but I can't. This light is, oh, time's up? Time's up. No lights.
Thanks.
Thanks.